Alright, let's take a step back from the machine shops and step onto the dock, because this next clip is about something that looks deceptively simple, but is actually a highly skilled trade that maritime workers spend years mastering. We're talking about rope work, specifically how to tie mooring lines, lashing lines, and tow ropes for large vessels. If you've ever been on a boat, even just a weekend fishing trip, you know that how you tie your lines matters. But when you scale that up to cargo ships, tugboats, and ocean-going vessels, the stakes are considerably higher. A knot that slips on a 50,000-ton container ship can cause millions of dollars in damage, or worse. Let's start with mooring lines. When a large vessel pulls into port, the deckhands throw heaving lines, lightweight ropes weighted at one end, to the dock workers, who use them to pull the heavier mooring lines ashore. These mooring lines are typically made from nylon or polypropylene, chosen for their stretch and UV resistance. The most common mooring knot is the bowline. It creates a fixed loop at the end of a line that won't slip or tighten under load. To tie it, sailors remember the old saying, "The rabbit comes out of the hole, goes around the tree, and back down the hole." Simple when you know it, life-saving when you need it. For lashing lines, used to secure cargo, lifeboats, and deck equipment, the cleat hitch is king. It's fast, it's strong, and it can be released quickly, even under load. You take 2 figure-8 wraps around the cleat and finish with a locking half hitch. Done right, it holds thousands of pounds without slipping. Now, towing is where things get really interesting. When a tugboat is pulling a barge or a disabled vessel, the tow line needs to absorb enormous dynamic loads, the surge and snap of waves and wakes. Tug captains typically use a large eye-splice in the tow line, which is dropped over a bollard on the vessel being towed. The tug end is secured to a towing bit using a series of figure-8 hitches, giving the deckhand the ability to add or release tension as needed. One critical trick experienced mariners use: always leave a tail. A few extra feet of rope past the last hitch gives you something to grab and adjust, especially in rough weather with cold or wet hands. Now here's a machine that commands respect. The FKB press brake you're looking at represents the pinnacle of sheet metal bending technology, designed for those jobs where precision meets serious size. What sets this beauty apart is the Bentronic control system. Think of it as the brain behind the brawn. This advanced software doesn't just control the bending process, it actually calculates springback compensation, material properties, and optimal bend sequences automatically. The operator inputs the desired angle, and Bentronic does the complex mathematics in milliseconds. Watch how smoothly that massive upper beam descends. The machine's synchronized hydraulic cylinders maintain perfect parallelism across the entire length, ensuring consistent bend angles, whether you're working the center or the edges of a 12-foot sheet. The back gauge positioning system, controlled with pinpoint accuracy, automatically adjusts for each bend in a multi-step sequence. This is the kind of equipment that shaped America's industrial backbone, now evolved for the modern era. If you've ever wondered what it looks like when a computer thinks in 3 dimensions, this is the clip for you. What we're watching is iMachining 3D technology in action, a revolutionary advancement in CNC programming that is genuinely changing the way complex parts are machined. The workpiece here is a detailed 3D model of an automobile. Not a full-size car, of course, but a precision machined scale replica made from solid aluminum, the kind of intricate model that automotive companies use for wind tunnel testing, design reviews, and presentations. iMachining 3D was developed by SolidCAM, and what makes it so remarkable is its intelligent toolpath algorithm. Traditional CAM software would calculate a set of parallel passes across the surface, efficient enough but not optimal. iMachining 3D instead generates swirling, morphing toolpaths that maintain a constant chip load throughout the cut. In plain English, the cutting tool is always removing material at the same rate, which means less heat, less tool wear, and dramatically faster cutting speeds. For a model as detailed as this automobile, with its curved hood, wheel arches, door contours, and windshield rake, the software needs to manage thousands of individual toolpath segments across complex compound surfaces. The machine's spindle tilts and rotates using its full 5-axis range to keep the cutting tool perpendicular to the surface at all times, ensuring the smoothest possible finish. The aluminum block is fixtured into the CNC machine the program runs, and over the course of several hours, fine aluminum chips curl away to reveal the shape of a car emerging from solid metal. It almost looks like magic. When complete, the model is deburred and polished, and the result is a showpiece of modern manufacturing precision. Every panel gap, every body curve, rendered in metal to within a few hundredths of a millimeter. This is what iMachining 3D can do, and it's genuinely stunning to watch. What you're about to see is a Sumitomo TFPA hot steel forging press, rated at an astonishing 5,000 metric tons of pressing force. Let that number sink in: 5,000 tons. Hot forging is one of the oldest metalworking techniques in human history. Blacksmiths have been hammering hot metal for thousands of years, but what you're watching here is that same ancient principle taken to an almost incomprehensible scale. The process begins with raw steel billets, thick cylindrical slugs of high-grade steel. These billets are loaded into industrial furnaces and heated to temperatures between approximately 100 and 500 degrees Celsius. At that temperature, steel doesn't melt. It becomes what engineers call plastic, meaning it's soft enough to be shaped under pressure, but still solid enough to hold its structure. The steel glows a bright orange-yellow, and at this point, it's moved quickly into the press before it has a chance to cool. The Sumitomo TFPA press is a closed-die forging machine. That means both the top and bottom halves of the die are shaped to the exact form of the finished part. When the press comes down with those 5,000 tons of force, the glowing steel has nowhere to go except into every corner of that die. Flash, the thin excess material that squeezes out around the edges, is trimmed away afterward. The result is a part with incredible mechanical strength. Unlike casting, where molten metal is poured and can contain air pockets, forged parts have a continuous grain flow that follows the shape of the component. That makes them stronger, tougher, and far more resistant to fatigue and impact. These presses produce components like crankshafts, connecting rods, axle shafts, and structural aerospace parts, pieces that literally hold civilization together. Today we're kicking things off with something that blends artistry and engineering in a way that would genuinely make your jaw drop. We're talking about 5-axis CNC milling of a robot face mask, and not just any milling process. This is done using SolidCAM, one of the most advanced CAM software platforms available in precision manufacturing today. Now, if you're not familiar with 5-axis machining, let me put it in simple terms. Traditional milling machines move in 3 directions, forward and back. left and right, and up and down. But 5-axis machining adds 2 rotational axes, which means the cutting tool can approach the workpiece from virtually any angle without ever stopping to reposition. SolidCAM makes this whole process smarter and more efficient through its iMachining technology. For now, what you're seeing on screen is the digital simulation, a virtual preview of every single toolpath before the machine ever touches the metal. The robot mask starts as a solid block of aluminum alloy. Engineers in SolidCAM first import the 3D CAD model, every curve, every hollow, every contour of that face. And then the software automatically calculates the most efficient cutting paths, recommending tool types, spindle speeds, and feed rates. What's fascinating here is the way the 5-axis head tilts and rotates to trace the organic curves of the face, the cheekbones, the eye sockets, the jawline. There's no flat surface here. Every inch of this mask is a compound curve, and the machine handles it all in one seamless setup. On the shop floor, the aluminum block is locked into the machine's vise, the CAM program is loaded, and the cutting begins. Coolant floods the work area to prevent heat buildup, and within a matter of hours, what was once a raw block of metal emerges, looking almost alive. The surface finish is smooth, precise, and ready for final polishing.